Okay, so this is section 3.3, quadratic functions and their properties. So here's some examples of quadratic functions, but technically a quadratic function is f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a is definitely not equal to 0. The domain of the quadratic function consists of all real numbers, because there is nothing we can't put in a quadratic. That's why he is so wonderful. Ax squared plus bx plus c, and this is the little equation we use for quadratic formula and all sorts of fun stuff. So the domain of a quadratic is all numbers. Alrighty. Okay, so let's apply some quadratics to our life here. Suppose that Texas Instruments collects the data shown in Table 1, which relate the number of calculators sold at the price P in dollars per calculator. Since the price of a product determines the quantity that will be purchased, right? If something's mega expensive, people won't buy as much of it. And if it's not very good quality and really cheap, that also they won't buy very much of those either. We treat the price as the independent variable. So in this case, where normally money goes on the y, we're actually putting money on the x-axis this time. The relationship between the number x of calculators sold and the price p per calculator may be approximated by the linear equation. X equals 21,000 minus 150p. Then the revenue R derived from selling X calculators at the price P per calculator is equal to the unit selling price P. So that it's equal to the unit selling price, our P value, times the number of X units actually sold. So revenue is price per calculator P times X, which is the number of calculators sold. So we're going to calculate revenue. Revenue is X times P.
So 11,160.
That would be for that amount. But we are going to have a revenue value that is generic for all amounts of calculators we produce. So if revenue is the price P times the amount sold X, R of P, we're going to replace X with 21,000 minus 150p. So X is now 21,000 minus 150p. And we're going to multiply that by P. And when we do, we get what kind of function?
Quadratic.
Quadratic, yeah. Not by accident, guys. Not by accident. Okay. Because revenue is the price per calculator times the number of calculators sold, X times P, it's 21,000 minus 150p, parenthesis, times P. And we get a nice little quadratic. Is it smiley face or frowny face? Does it smile up or does it frown down?
It would go down.
It is frowny face because we got a negative value out in front of our squared term. And there's the picture. Go ahead and sketch this picture onto your graph. So no calculators means no revenue. As we increase, we reach our maximum revenue right about here. It's right about $70. And then we start losing revenue until we get to 140. That's an expensive calculator. All right, a second situation in which the quadratic function appears involves the motion of a projectile, like this cannonball. Based on Newton's second law of motion, force equals mass times acceleration, or F equals ma. It can be shown that, ignoring air resistance, the path of a projectile propelled upward at an inclination to the horizon is the graph of a quadratic function. See Figure 2 for an illustration. Later in the section, we shall analyze the path of a projectile. What? All right, so our first learning objective is to graph a quadratic function using transformations. We should be amazing at this because we rocked the heck out of those transformations last chapter. So, go ahead and make a nice little sketch of these quadratic functions when I change the a value in a quadratic. So for f of x equals ax squared, for a greater than 0, I have my parent function when a equals 1. That's that blue one in the middle. When a equals 1/2, it spreads and makes my quadratic wider. When a equals 3, it makes my quadratic taller and skinnier. We talked a little bit about this for our revenue problem. When a is negative, it makes a frown. But the same rules still apply even though we're reflecting across the x-axis. It's still a fatter curve when you have 1/2. It's still a skinnier curve when you have a number whose absolute value is greater than 1. Okay. Moving along. So a graph of a quadratic function is going to have an axis of symmetry, and it's going to have a vertex, which is either going to be the lowest point if a is greater than 0, or it's going to be the highest point if a is less than 0. So if I have a negative value in front of my x squared, I'm going to be opening down, and my vertex is going to be at the highest point. If I have a positive value, I'm going to be opening up, and my vertex is going to be at my lowest point. All right, so graphing a quadratic function using transformations, we are going to graph the function f of x equals 2x squared plus 8x plus 5. We're going to find the vertex and the axis of symmetry. So the first thing we're going to do is we're going to convert this from polynomial form to vertex form, and we're going to do that by completing the square. So we're going to rewrite this. We're going to pull out, the first thing we're going to do is pull out the 2, because if we look at the general form of our parabola, our x value inside the parentheses doesn't have a coefficient, so that we have to pull out the 2. So it's going to, instead of being 2x squared, we're going to go 2 parentheses x squared. We're pulling out that 2, so we need to divide our 8x by 2 to get 4x. And then we're going to add a multiplier so we can, this is the completing the square part. Remember in Algebra 1 where we did completing the square and it didn't make any sense because we're like, why would I ever use this? This is lame. Oh, we're using it all the time now when we want to find equations of circles and we want to find the vertex form of a parabola. We end up completing the square. Okay, the plus 5, he stays here, and I'm going to, whatever value I add here, I'm going to multiply that by 2, and I'm going to subtract it because in order to keep an equation, whatever I add, I have to also subtract.
So is the number that you're going to complete?
Okay, so we're going to complete the square and find this value here. When I put it in here, I'm also going to put it here at the end of my equation. So 4 divided by 2 is 2, and 2 squared is, so right here, in order to complete the square, you always take your b term divided by 2 and square it. So the 4 goes inside my parenthesis, and it's also going to go here. So essentially, I am adding 8 to this equation, so I got to subtract 8 as well. Otherwise, I won't have an equal equation. So once I complete the square, I can rewrite this as a perfect square. This is x plus 2 squared. So the reason we do that is so we can write this in vertex form, and now we can see my vertex is at -2, -3. I'm opening up, and I can find my axis of symmetry. It's going to be at x equals -2.
How did you get from...
Okay, so our quadratic parent function is y equals x squared. It has this nice shape. We are actually going to apply these transformations to it. We're going to give it a vertical stretch of 2, so make it twice as skinny. So instead of going over 1, up 1, we're going to go over 1, up 2. Then we're going to shimmy shift this 2 units to the left, because our plus 2 here means 2 units to the left. And then lastly, we're going to shift it 3 units down. So the -3 means 3 units down. So our vertex ends up being at -2, -3. And our axis of symmetry is x equals -2. This isn't x minus, there should be an equal sign there. It got overwritten by the picture. So our axis of symmetry is x equals -2, and our vertex is at -2, -3. All right, so this is the proof for the vertex form. We're going to put together a little equation. So instead of having to go complete the square every time, I'm going to give you a vertex formula. So you can go straight from multiplied form to vertex form. So we don't have to complete the square every time. So H, so write this down, and you guys get a highlighter out, get your star, put a box around this. If f of x is equal to ax squared plus bx plus c, which is also equal to a parenthesis x minus h close parenthesis squared plus k, we can find h and k by using these formulas. H is equal to -b over 2 times a. And k is equal to 4ac So it's 4ac minus b squared divided by 4a. So if you guys can remember, H and K are the vertex. Yes. So if you guys can remember this one, you can always plug it in to find the K. All right, so now we're going to take that property and we're going to identify the vertex and axis of symmetry of a quadratic function. Our vertex is going to be at negative b over 2a, and the other one is going to be at, whatever our function equals when we plug in the x-coordinate for our vertex. So I don't have the, we wrote it down before, but I don't have the k memorized for my function because I can always calculate it back out. All right, so the vertex is at negative b over 2a, comma, whatever our function is when we plug in negative b over 2a. Our axis of symmetry is always the line x equals negative b over 2a. The parabola opens up if a is positive, and the parabola opens down if a is negative.
This is just another way how to.
All right, without graphing, we're going to locate the vertex and axis of symmetry of this parabola and figure out, does it open up or down? I can figure out. Guys, we can figure out if it opens up or down. Yeah. This guy's a happy guy. He's got a positive a value right here in front of the x squared, so he opens up. All right, so let's apply the vertex equation. So our b value is negative 3, our a value is 2. So we're going to put that in. So minus a negative 3 is 3, and 2 times 2 is 4. So our vertex is at, the x-coordinate for our vertex is at 3/4. I'm going to plug 3/4 in here for x to find my y-coordinate for my vertex. So 3/4 squared, actually we're squaring functions, minus 3 times 3/4 plus 2. So this is 9/16. Huh? Okay. 9/16 times 2 is 9/8. So we have to square it and then multiply it by 2. 3/4 times 3 is 9/4, and 2 is 2. When we find a common denominator, add this, subtract this, and add this, we get 7/8. So the vertex is at 3/4, comma 7/8. And our axis of symmetry is going to be at x equals 3/4. And we are going to be opening up. All right, so we're going to graph a quadratic function using its vertex, axis, and intercepts. Graph a quadratic function using its vertex, axis, and intercepts. So we're going to look at the discriminant of our quadratic function to tell us how many x-intercepts it has. So this is the inside, when you have your quadratic equation, so negative b plus or minus square root of b squared minus 4ac all divided by 2a, quadratic formula. This is the inside underneath the square root. So we're just going to take the b squared minus 4ac part. So the part that lives underneath the square root in our quadratic formula from old school days. So if our discriminant, or that part that is underneath the square root, is greater than 0, then we have two x-intercepts. If our discriminant is equal to 0, so then it goes down, touches our vertexes on the x-axis. So it has, if our discriminant is equal to 0, we have one x-intercept, and our vertex is actually sitting on the x-axis. It's awesome. And if our discriminant is less than 0, so that means if our x and our y are hanging out here, and our graph maybe opens up, but our vertex is above the x-axis, so it never touches the x-axis, then we have no x-intercepts. So we're going to use the discriminant to give us an idea of how many times our parabola touches the x-axis. So discriminant greater than 0 crosses twice. Discriminant equal to 0 touches once, and discriminant less than 0 does not touch at all. Here is a picture. If you need to sketch a picture, you may, but so here's what it looks like. When you have two x-intercepts, it's either a positive that with a vertex that's below the x-axis. If you're on the x-axis, you have one x-intercept, and if you're above the x-axis, you have no x-intercepts. So this is just a picture to go with what we just wrote down. So go ahead and do a sketch next to each of the discriminants you just wrote down. All right, let's do an example. F of x equals 2x squared minus 3x. We're going to use the information from the previous example and the locations of the intercepts to graph our function. So remember, our vertex ended up at 3/4, 7/8. Our axis of symmetry is x equals 3/4. So if we graph that on a graph, it's right there. We know our graph opens up. And if our vertex is above the x-axis and it opens up, then we're not going to have any x-intercepts. Boo-hoo. When we plug in 0 for x, we get a y-intercept of 2, so let's put that on our graph. We know if we mirror that over our axis of symmetry, we have this same point on the other side. So if this is 3/4 away, we're going to go 3/4 on this side and graph that point and put our parabola in. So we're just collecting the vertex, the axis of symmetry, and our intercept so we can put together a clear graph of our function. All right, let's graph another function, 2x squared plus 4x minus 1, by determining whether the graph opens up or down, and by finding its vertex, axis of symmetry, and x and y intercepts. So we have that negative b over 2a. I don't know why they have an x here. This should be a, negative b over 2a. So negative 4 over 2 times 2 gives us negative 4 over 4, or negative 1. So our vertex is at negative 1, and I need to find what my y value is when x is equal to negative 1. So I'm going to plug it in. So negative 1 squared is 1, times 2 is 2, plus 4 times negative 1 is minus 4. So 2 minus 4 is negative 2, and then minus 1 more is negative 3. Yeah, so it's going to be right. Negative 1, negative 3. My axis of symmetry is at x equals negative 1. We are opening up or down? Up. So I'm going to be a smiley face. And we are, it's by a factor of 2. So instead of going over 1, up 1, we're going to go over 1, up 2. We have a y-intercept at negative 1. We find that by plugging in 0 for the x. So at negative 1, there's a nice point. I have its matching point mirrored on the left-hand side of my axis of symmetry. And then I throw down my nice parabola. If I set my function equal to 0, I can find my x-intercepts. We have to use the quadratic formula to do that. So we got negative b plus or minus square root b squared minus 4ac all divided by 2a. So if I plug in 4 for b, 2 for a, negative 1 for c, simplify, simplify, simplify that down. I get that my x-intercepts are at negative 2 plus or minus root 6, all divided by 2, which are around here. So it's at about negative 0.22 and, or sorry, 0.22 and negative 2.22.
So how do you find the y values?
It's at 0.
Just all of them are.
This one is because we set it to 0. The domain of a quadratic is all real numbers. And then this guy has a range. Well, he's got a minimum. The smallest he can go is negative 3. And he's just going to go on and on to infinity forever. So he gets negative 3 included, comma, infinity. It is decreasing from negative infinity to negative 1, then increasing from negative 1 to infinity. All right, so we're going to find the quadratic function given its vertex and one other point. So vertex form is f of x equals a parenthesis x minus h squared plus k. So they're going to give us the vertex so we can fill in h and k. And we're going to plug in our point, the x and y values, so we can find our a. Once we have the a, we plug it back into the equation. It's like finding the slope-intercept form when we're given a point and the slope of a line. Okay, so we have a vertex at negative 2, 3, and our y-intercept is at 1. The y-intercept at 1, what's our coordinate to represent y-intercept at 1? It's the coordinate that goes with it. So it's going to be 0, comma 1. So we're going to go ahead and plug in negative 2. So x minus negative 2 is x plus 2. And positive 3 here for h and k.
Is this the completing the square?
This is just plugging in vertex into vertex form. Yeah. So a y-intercept at 1 means that my y value, or my f of x, is equal to 1. So where f of x was here, now it's going to be 1. My x value, when y is 1, is at 0. So that's why I have a 0 plus 2. I'm going to square that and add 3. So I've got 1 equals a times 0 plus 2 squared plus 3, because I'm plugging in my point so I can find out what my a value is. So I get 1 equals 4a plus 3. Subtract 3 from both sides. Divide by 4. So 1 minus 3 is negative 2. Negative 2 divided by 4 is negative 1/2. So now I can go back to my vertex form of my equation. So I'm going to plug in negative 1/2 for my a, x stays, plus 2 parentheses squared, plus 3. So we use that point to find our a value. All right, when you find the maximum or minimum of a quadratic function, you are just finding the vertex of that quadratic. So use the same processes we've gone over to find the vertex.